Welcome to this complete visual guide on PySpark, where we'll journey from the fundamental building blocks of distributed data processing all the way to real-world machine learning applications. This presentation is designed to be beginner friendly, meaning if you've never touched big data tools before, you'll be able to follow along comfortably. It's also hands-on, so you'll see actual code examples along the way, and it's grounded in a real-world use cases, so you understand not just the theory but how companies actually use PySpark in production today. Let's start with the basics. PySpark is essentially the Python API for Apache Spark. In other words, it's the bridge that lets Python developers tap into Spark's powerful processing engine using the language they already know and love. Now, why do we even need something like this? The answer lies in scale. When your dataset becomes too large to fit into the memory or processing power of a single computer, you need a way to spread that work across many machines working together. This is called a cluster. PySpark lets you analyze datasets that would be completely impossible to handle on just one machine. It's important to understand the relationship between PySpark and Spark itself. Spark's core engine is actually written in Scala and runs on the Java virtual machine. PySpark simply gives Python developers a friendly, familiar way to access that same powerful engine without needing to learn Scala. Finally, one of the biggest advantages of PySpark is that it's a unified engine, meaning batch processing, real-time streaming, SQL queries, and machine learning all live under one single framework. You don't need four different tools. PySpark handles all of it. Now, why PySpark? Now let's talk about why PySpark has become so popular in the industry. The first big reason is blazing speed. PySpark performs in-memory computing, which means it keeps data in RAM rather than constantly reading and writing to disk. This design can make it up to 100 times faster than traditional disk-based data processing tools. The second reason is elastic scale. You can start small running PySpark on your own laptop and then scale up to a cluster of thousands of nodes all without rewriting your code. That flexibility is incredibly valuable as your data grows. Third, PySpark is distributed by nature. Your workload is automatically split into smaller pieces and processed in parallel across every machine in the cluster, dramatically cutting down processing time. And lastly, PySpark is Python friendly. It offers data frames that feel very similar to pandas. So if you already know pandas, the learning curve is much gentler and you also get access to Python's massive ecosystem of libraries. Now let's come PySpark architecture. This slide takes us under the hood to understand how PySpark actually works behind the scenes. There are three key components. First, the driver program. This is the brain of the operation. It hosts something called the Spark context, which acts as the entry point for your entire application. This is where your code starts running and where the overall execution plan is created. Second, the cluster manager. Its job is to allocate resources, meaning it decides which machine in the cluster will do the work and how much memory and processing power each one gets. Third, we have the executors in this diagram. We see executor 1 and executor 2. But in a real cluster, there could be many more. Each executor actually runs the task assigned to it and can cache data in memory for faster access later. To summarize the flow, the driver coordinates all the work, the cluster manager assigns the necessary resources, and the executors do the actual heavy lifting by running tasks in parallel and sending the results back. Now let's come to RDD, Resilient Distributed Dataset. RDD stands for Resilient Distributed Dataset, and it's the original core abstraction that PySpark and Spark are built on. Let's break down what that means. By definition, an RDD is an immutable collection of data once created. It cannot be changed and it's partitioned, meaning it's split into chunks that are processed in parallel across the cluster. The word resilient is key here. If a partition of data is lost due to a machine failure, Spark can automatically rebuild it using something called a lineage graph, which is essentially a recorded history of how that data was derived. This makes RDDs fault tolerant by design. Now, RDDs support two types of operations. The first is transformations like map, filter, and flat map. These are lazy operations, meaning they don't execute immediately. Instead, they simply build up a plan of what needs to happen. The second type is actions like collect, count, and reduce. These are what actually trigger execution and return real results to you. This leads us to the RDD lifecycle shown on the slide. You start with your raw data, you apply lazy transformations to build your processing plan, and finally an action triggers everything to run, producing your final result. After that, data frames in PySpark. Data frames are a more structured and user-friendly way to work with data in PySpark. Think of a data frame as a distributed table. It has named typed columns, very similar to a spreadsheet, except this spreadsheet can span across an entire cluster of machines rather than sitting in one file. The example on the slide shows a name and city, a clean, organized structure that's easy to query and understand. One major advantage of data frames over raw RDDs is speed. Data frames are optimized by two powerful components: the catalyst optimizer, which intelligently plans the most efficient way to execute your query, and the tungsten engine, which optimizes memory and CPU usage under the hood. Together, they make data frame operations significantly faster than working directly with RDDs. On top of that, data frames offer a simple expressive API. You can perform operations like select, filter, and group by in a style that feels very similar to SQL, making it intuitive even for those coming from a database background. Spark SQL. Spark SQL is a feature that lets you interact with your data using the SQL language you may already know. instead of only writing data frame code. The first concept here is registering views. You can take any data frame and expose it as a temporary SQL table or view, which allows you to query it just like you would a database table. In the code example, we see df.create or replace temp view sales. This line takes our data frame and registers it under the name sales. Next, we can run SQL directly on this data as shown. We use spark.sql with a standard SQL query that selects the region column and sums up the amount column, grouping the results by region. This is genuinely powerful because it means massive distributed datasets can be queried using the exact same SQL syntax you'd use on a small local database. Lastly, Spark SQL is interoperable. You're not logged into choosing either SQL or data frame code. You can freely mix both approaches within the same pipeline using whichever style is more convenient at each step. Now, PySpark versus Pandas. This comparison slide helps you decide when to use PySpark versus when to stick with Pandas. Looking at data size, Pandas is built for data that fits comfortably in memory. Think megabytes to a few gigabytes, while PySpark is designed for big data, handling gigabytes all the way up to petabytes. In terms of compute, Pandas runs on a single machine using just the resources of your one computer, whereas PySpark distributes the work across an entire cluster of machines. When it comes to speed of scale, Pandas start to slow down significantly as data grows larger, while PySpark maintains parallel processing and stays fast even as datasets become massive. Finally, in terms of best use case, Pandas shines for exploration and working with similar datasets. Quick interactive analysis, while PySpark is built for production environments, handling large-scale data. The rule of thumb to remember is simple. Use Pandas for small interactive work and switch to PySpark once your data outgrows what a single machine can comfortably handle. Now, machine learning with MLib. MLib is MLib is Spark's built-in library specifically designed for scalable machine learning, meaning you can train machine learning models on datasets that are far too large for traditional single machine ML libraries. It follows a clean structured workflow. You prepare your data, train a model on it, evaluate how well that model performs, and then use it to make predictions. A great real world example of this is building a product recommendation system at scale using an algorithm called ALS or alternating list squares, which is specifically designed for these kinds of recommendation problems. The ML pipeline shown on the slide breaks this down into five clear stages. First, you ingest the raw data, then you extract meaningful features from it. Next, you train your model on those features, then you evaluate the model's performance to see how accurate it is, and finally you deploy it so it can be used in real applications. Now, real world use cases. This slide brings everything together by showing how PySpark is actually used across different industries. In banking, PySpark powers fraud detection. Financial institutions scan millions of live transactions in real time to flag unusual or suspicious activity before it causes damage in e commerce. PySpark drives recommendation engines. By analyzing customer behavioral data, companies can personalize product suggestions for every single shopper, improving the overall shopping experience and boosting sales. And in operations, PySpark is used for log analysis. Organizations process enormous volumes of log files and clickstream data to uncover valuable operational insights like identifying bottlenecks or security issues. The overarching message here is that PySpark is one single engine capable of powering meaningful analytics across many different industries. Wherever data has become too large for a single machine to handle. Now, basic PySpark code example. Now, let's walk through an actual hands-on code example broken into three simple steps. Step 1 is setting up. We start a Spark session which is required before doing anything else in PySpark. The code imports Spark session from PySpark.sql and then builds a session using .builder, giving it an application name with .app name my app and finally calling .get or create to either create a new session or reuse an existing one. Step 2 is loading the data. Here we use spark.read.csv data.csv header equal to true to read a CSV file into a data frame with header equal to true, telling Spark that the first row of the file contains column names rather than actual data. Step 3 is transforming and displaying results. The code filters the data frame to keep only rows where the salary column is greater than 50,000, then groups the remaining data by the department or column. Department column counts how many records fall into each group, and finally calls.show to display the results. This simple three-step pattern, setup, load, transform, is the foundation of almost every PySpark script you'll write. Advantages and limitations. Every technology has trade-offs and PySpark is no exception. On the advantage side, we have four key strengths: fast in memory processing, that speeds up computations dramatically, the ability to scale to massive datasets that would overwhelm traditional tools, a unified API that combines batch processing, SQL, and machine learning all in one place, and a huge open source ecosystem with strong community support and countless integrations. On the limitations side, we also need to be realistic about the challenges. Setting up a cluster involves real overhead in terms of time and infrastructure. PySpark can be memory hungry on large jobs if if not configured carefully. There's a steeper learning curve compared to simpler tools, especially for beginners. And finally, PySpark can genuinely be overkill for small data sets If your data fits comfortably in pandas, there's often no need to bring in the added complexity of a distributed system. The future of PySpark. Looking ahead, PySpark's role is only growing. It's becoming the backbone of AI and machine learning workflows, feeding and preparing massive datasets that are used to train large scale models. It's also central to real time insight with structured streaming enabling instant, always on analytics rather than just periodic batch reports. PySpark sits at the core of cloud native computing too. It's the engine driving major platforms like Databricks, AWS EMR, and Google Cloud's DataProc, all of which are heavily used in enterprise environments. And because of all this, PySpark skills are in high demand. It's considered one of the top skills for anyone pursuing a career in data engineering or analytics today. Let's wrap up everything we've covered. PySpark is powerful. It brings distributed big data processing capabilities while keeping the simplicity and readability of Python. It's versatile, offering RDDs, DataFrames, SQL querying, and machine learning, all within a single unified engine. It's practical, proven across real industries like finance and retail, and used extensively in large scale operational environments. And most importantly, it's future ready as AI and data driven decision making continue to grow. PySpark stands out as an essential skill for anyone looking to work in this space. So that brings us to the end of this presentation. You now have a clear structured path starting from PySpark's fundamentals, moving through its architecture and core concepts like RDDs and data frames, and finally arriving at real world analytics and machine learning applications. Thank you for following along, and let's keep exploring the world of big data together.